In this video, we will be differentiating inverse trigonometric functions. We begin with theorem 5.18, which gives us the chain rule version of the 6 derivative rules for the inverse trig functions. And now we will look at some examples where we apply those rules to differentiate inverse trig functions. In our first example, our u, the input to arc sine x, which is the same thing as sine inverse, is equal to 2x. U prime is then simply 2. Now we will be applying the first rule to take the derivative of this inverse trig function. So we have u prime, which is 2, divided by the square root of 1 minus u squared. U squared will be 4x squared, leaving us with our final answer. In our second example, u, which is the input to arc sine, is the square root of x. U prime, its derivative, is 1 divided by 2 root x, and u squared is simply x. So now we begin filling this out to get our derivative. So in the numerator, we have u prime, which is 1 over 2 root x, and in the denominator, we have the square root of 1 minus u squared, leaving us with 1 minus x. I'll do some algebra to simplify this and leave us with 1 over 2 root x multiplied by the square root of 1 minus x. We can then combine these two factors, since they're both under the square root, to be left with 1 over 2 multiplied by the square root of x minus 1 over x as our final answer. In our next example, u, which is the input to arctan, is 3x. Our u prime is simply 3, and our u squared is 9x squared. So now we will be filling out this expression to get the derivative of that arctangent function. We have u prime in the numerator, which is simply 3, and then in the denominator we have 1 plus u squared, which is 1 plus 9x squared. Moving on, our u is now e to the 2x. That is the input to this arcsecant function. We will need u prime. Chain rule tells us that is 2e to the 2x. And we will also need u squared, which will be e to the 4x. We will now begin to fill this out to get our answer for this derivative. In the numerator, we have u prime, which is 2e to the 2x. In the denominator, we have the absolute value of u, which is the absolute value of e to the 2x. And then that is multiplied by the square root of u squared, which is e to the 4x, minus 1. E to the 2x is always greater than 0. So this absolute value of e to the 2x is the same thing as e to the 2x, meaning that these two factors here can cancel out and leave us with our final answer of 2 divided by the square root of e to the 4x minus 1. Moving on to our last example, we have the derivative of a sum. We're going to need to take the derivative term by term. For the first term, our u is simply x. So we don't need to use the chain rule because u prime is simply 1. Using our derivative rules from above, we see that the derivative of the first term is 1 divided by the square root of 1 minus x squared. And I'm getting that from this rule here, with u simply being x. To take the derivative of the second term, I'm going to need to use the product rule, where f is x and g is the square root of 1 minus x squared. I'll take f prime and g prime. Make sure that you use the chain rule when you're taking g prime to end up with a negative 2x divided by 2 multiplied by the square root of 1 minus x squared. So I'm using the chain rule or the general power rule there. I'll simplify g prime by canceling out the 2's and leaving us with negative x divided by the square root of 1 minus x squared. So now I'll go back here and fill out f prime multiplied by g added to g prime multiplied by f. G prime is negative, so this will be a minus sign in here. The first term and the last term do have a common denominator, and so I can combine them into 1 minus x squared divided by the square root of 1 minus x squared. And then I can simplify this first term because all of this here in the numerator is raised to the first power, and it's divided by the same thing raised to the 1/2 power, which will just leave me with 1 minus x squared raised to the 1/2 power, which is added to itself to leave us with a final answer of 2 times the square root of 1 minus x squared.